Let's review chapter 10 on graphs. What are the main ideas we need to remember? All right, so graphs, they're vertices and edges. So every edge has a vertex at each end, so two endpoints. So this is a simple graph. A more complicated graph is a multigraph that allows more than one edge between two vertices. And a pseudograph allows multiple edges and also loops. But this one is just simple. And a directed graph means every edge has a direction indicated by an arrow. The degree of a vertex in a graph is the number of edges that have it as an endpoint, where loops add 2 to the degree. All right, so for each vertex, just look at how many edges are coming out of that vertex. That's basically the degree. So here's an example. So this graph has 6 vertices, A, B, C, D, E, and F. And we want the degree of every vertex, and then add up all those degrees to get the total degree. So the degree of A is a 1, it's the endpoint of just one vertex. Degree of B is 3. You can see 3 edges. The degree of C is 5. So 3 regular edges, and then a loop adds 2 more. All right, so you get the idea. So 2, 5, degree of F is 0, and no edges. And if you add those up, the total degree of G is 16. We saw a theorem about the total degree. So the handshaking theorem says that the total degree is always equal to twice the number of edges in any pseudograph. And so we can check that here. The total degree is 16, so the theorem says there should be 8 edges. Let's check. So 1, 2, 3, 4, 5, 6, 7, 8. Looks good. Okay, we looked at different families of graphs, and they have special notation. So capital K subscript n is the complete graph on n vertices. So n vertices, and then draw in all possible edges, keeping it simple. C sub n is the cycle graph, so just like a circle. And then if you add a new vertex in the middle of Cn and connect edges like spokes, you get the wheel graph. Yeah, it's a bit confusing. So W sub n has n plus 1 vertices. So it looks like C sub n, but just with one extra vertex in the middle. Q sub n, those are the cube graphs. with 2 to the n vertices. So Q2 is the square, Q3 is the cube. And K subscript n comma m. And so if we see 2 numbers down here, that's a complete bipartite graph. It's going to have n plus m vertices, and then all possible edges between the n vertices and the m vertices. So examples here, yeah, this is K sub 5. C sub 5 looks like this. And then add a new vertex in the middle to get W sub 5. And K2 comma 5, the complete bipartite graph. You're starting with 2 vertices over here and 5 over here, and then make all connections between this group and this group. So in general, a graph is bipartite if its vertices can be made into 2 groups so that every edge has its endpoints in each of the 2 groups. A good way to check if a graph is bipartite is to see if you can color it, color its vertices using at most 2 colors. And you want to color it so that edges only connect vertices of different colors. Yeah, we'll look at coloring more, but just coloring with 2 colors. So let's look at this first graph. So here, can we color this with 2 colors? Well, we can make this orange. So if this is orange, then this has to be stay white. Make this orange and this orange. Okay, so we were successful here. So we colored the vertices orange and white, and every edge is connecting 2 vertices of different colors. Okay, so that tells us that this graph is bipartite. If we try to do the same thing here, so what goes wrong? Yeah, so looking at this square, we have to do it like this, but then there's a problem. Now this vertex is connected to a white and an orange, so it has to be a 3rd color. Yeah, so anytime you have a triangle, then yeah, it's not going to be bipartite. Okay, so you see the difference. So if I leave this white, then it's connected. I've got an edge connecting 2 whites. Or if I color it orange, I have an edge connecting 2 oranges. So there's no way to color this just with 2 colors so that every edge connects different colors. And yeah, going back to our definition, yeah, so the groups here would be you could group the orange vertices into one group, the white vertices into another group, and those are the 2 groups you need. All right, next topic, graph isomorphism. 2 graphs are isomorphic if they're really the same. In other words, the same connections, they might be drawn differently. For example, K sub 4, the complete graph on 4 vertices, looks like this. W sub 3, the wheel graph, basically it's C3 with an extra vertex in the middle, looks like this. And these are really isomorphic. Can you see the isomorphism? Can you see why they're really the same? Yeah, I mean they're both 4 vertices, and you have all possible connections, all possible edges connecting those 4 vertices. For example, yeah, if you move this vertex into the middle of this triangle, then it would look more like this. Yeah, so maybe that's a difficult example. So if 2 graphs have different numbers of edges, or different numbers of vertices, or different degree lists, then they're not isomorphic. There's no way to redraw them to look the same. Yeah, you do have to be careful though. You can have graphs that do have the same number of edges, vertices, and the same degree lists that are not isomorphic. Here's an example. So here's G, here's H. They have they both have 7 vertices and 6 edges. The degrees, their degree lists are also the same. For pendant vertices, 4 vertices of degree 1, 1 vertex of degree 2, and 2 vertices of degree 3. But these 2 graphs are not the same. Yeah, one way to see they're not the same is this graph H has 2 vertices of degree 3 that are adjacent, that are connected by an edge. But if you look at the 2 vertices of degree 3 in G, they're not adjacent. They're not connected by an edge. All right, so these 2 they're 2 different graphs. They're not isomorphic. That's one way to see. Example 2, show that these 2 are isomorphic, G1 and G2. All right, so I've tried to make them look different by drawing them differently, but I hope you can see these are really the same. Okay, so they certainly have the same number of vertices, edges. The degree lists are the same, 1, 2, 3, 1, 2, 3. And yeah, so if you move this B up here and move this X up here. Okay, so we want to show that these graphs are isomorphic. So the first step is to kind of make them look the same. Then we can see what matches with what. All right, so drawing them like this, yeah, we see they really are, they do look the same, but we want to prove it. So the way to prove it is to set up this matching function f. Okay, so what matches with what? So yeah, so A, this degree 3 vertex matches with this degree 3 vertex. So we want to match A to Y. So f of A equals Y. F of B equals X, and f of C equals Z. Okay, so this is a one-to-one and onto function that matches up the vertex sets. Now we want to show that f preserves the connections. Okay, so two vertices are adjacent in G1 if and only if f sends them to two adjacent vertices in G2. So to check that condition, the best way to do it is to use adjacency matrices. Okay, so take the order ABC and draw the adjacency matrix for the first graph, G1. All right, so we're just putting in the number of edges connecting each pair. All right, so there's a 0 here because there are there's no edge connecting A to A. There's one edge connecting A to B. So we put a 1 here. And there are two edges connecting A to C. So we put a 2 here. Also B to A, yeah, there's 1. And C to A, there's 2. No edges from B to B, no edges from B to C, or C to C, so these are zeros. And now do the adjacency matrix for G2, but use the corresponding order. So instead of X, Y, Z, we need Y, X, Z. So this is what matches. Okay, and then make the adjacency matrix, and you'll see, yeah, we get the same numbers in the same places. And so the fact that these are the same tells us that G1 is isomorphic to G2. So we've proved it. All right, so that's how to show that two graphs are isomorphic, that they're really the same. Yeah, it's usually easier to show two graphs are not isomorphic, if they have different degree lists, for example. All right, so we use these adjacency matrices. And they're also useful for counting paths. I guess we're going slightly out of order here. So yeah, path is just a sequence of edges, a sequence of connected edges in a graph. Yeah, the length of a path is just the number of edges. So if you're counting paths, one way to do it is to take the nth power of the adjacency matrix of the graph. Yeah, we can look at this graph, G1. So that nth power counts the paths of length n in G1. For example, yeah, so the simplest thing we can do is take the second power of the adjacency matrix, so that's this matrix multiplied by itself. All right, multiplying matrices, it's the rows times the columns. So 0 times 0 plus 1 times 1 plus 2 times 2 is 5. Okay, so multiplying the first row by the first column, put the answer in the first row in the first column here. How about the second row times the first column? Well, that's 1 times 0 plus 0 times 1 plus 0 times 2. Those are all zeros, so the answer is 0. And yeah, the third column times the first row, yeah, it's the same thing. 2 times 0 plus 0 times 1 plus 0 times 2 is also 0. And then multiply these three rows by the middle column, the second column, and you get these three numbers, and then these three numbers for the third. Okay, here I put back in the vertices. So yeah, this 5, for example, this 5 is telling us that there are 5 paths of length 2 from A to A. Okay, this 5 is in the row corresponding to A and the column corresponding to A. Yeah, this 2 is because we have a second power. If you look at row C, column B, so how many paths of length 2 are there between C and B? Well, there are 2. Okay, so all these numbers here are counting paths of length 2. Let's go back to our graph. Yeah, we could use this one or the original. Maybe it's clearer here. So 5 paths of length 2 from A to A. So starting here, yeah, so here's one path. Just go to B and then come back. That's 1. You could go to C and then come back on the same edge. That's 2. Go to C, come back on a different edge. That's 3. Go to C on this edge, come back the same way. That's 4. Or go to C and come back this way. That's 5. All right, yeah, so yeah, there are 5 paths of length 2 from A to A. And yeah, you can see there are 2 paths of length 2 from B to C, going this way or going this way. Okay, so powers of the adjacency matrix lets you count paths. Yeah, if you're counting paths of length 3, you need to multiply by another A sub G1, so you need a third power to count paths of length 3, fourth power for paths of length 4, and so on. Yeah, so maybe we should have done this first. So yeah, so now looking at paths and circuits, yeah, so a path, what we were just talking about, paths look like this. So just a sequence of vertices connected by edges. The number of edges, that's the length of the path. Yeah, this is a path of length 5 from A to B. Yeah, there are 6 vertices, but it's the length is the number of edges. A path is simple if it does not use an edge more than once. And so if it uses an edge twice or three times, it's not simple. Path is a circuit if it finishes where it starts at the same vertex. More terminology, a graph is connected if there's a path between any two vertices. Is example 1 connected? Way back to example 1. Yeah, so this is, so for this graph, is there a path connecting every two vertices? No, so you can see if you want to get from F to any other vertex, there's no way to do it, there's no path. So G is not connected. Of course, G has two connected pieces, so it has two connected components, F and the rest. Okay, so you can break up any graph into connected components. Okay, next, an Euler path is a path in a graph that uses every edge exactly once. Okay, so it's necessarily simple, but it uses every edge. And an Euler circuit, that's the same thing, just gets back to the beginning. And we have these two nice theorems. It's classic graph theory. The first one, a connected multigraph has an Euler circuit if and only if every vertex has even degree. So that's the theorem for circuits. The same thing if you're looking for Euler paths, then two of the vertices can have odd degree, most two. And the path must start and finish at those odd degree vertices. All right, so if you have a graph with two odd degree vertices, yeah, then it does not have an Euler circuit, but it does have an Euler path. Let's look at these two graphs. So does G have an Euler circuit or an Euler path? Let's check the degrees. So here, degree 4, 4, 2, 2, 2, and 2. Yeah, so all the degrees are even. So this graph G has an Euler circuit according to the theorem A. Can we find it? Yeah, so maybe so you can start anywhere. How about here? So we're using every edge exactly once and getting back to the start. Yeah. Okay, yeah, all the vertices even, so it has an Euler circuit. Yeah, you can see these two guys are degree 1, so this graph does not have an Euler circuit according to the theorem. It's got some odd degrees. But only two odd degrees. So then theorem B says there is an Euler path. No Euler circuit, but there is an Euler path. And the path must start and finish at the odd degree vertices. So let's start here. Could go this way and here. Okay, we used every edge and got an Euler path. All right, yes, that's a nice question. Find Euler circuits and paths. We also briefly looked at Hamilton paths and circuits. So those, instead of crossing every edge once, they pass through every vertex exactly once. And in the last sections, we looked at shortest paths. Now, yeah, we're changing the idea of length slightly here. So now we're talking about weighted graphs. So every edge has a number. And then the length of the path now, instead of the number of edges, it's the sum of the weights of the edges. Okay, so if I give you two vertices on a weighted graph, can you find the shortest path? I hope this is visible. And so we're looking for a path here between A and H with the smallest sum of numbers. For example, if you go this way, 6 plus 1 plus 10. So this path has length 17. But maybe we can do better. And yeah, I see some small numbers here. There's a 1 and a 1. Well, yeah, you can, if you go this way, 3 plus 2 plus 1 plus 10 is 16. And yeah, can you find 15? You could try the top, but yeah, actually, if you just go straight across, yeah, 3 plus 9 plus 3 is 15. Yeah. And so I think that's the best you can do. So the shortest path here is from A to C to F and then to H. And has length 15. All right, so that's what we're looking at in this section. We studied Dijkstra's algorithm, so that gives an efficient method. It's a bit awkward doing it by hand, but it's certainly easy to program. And finds the shortest path. So yes, I do review that Dijkstra's algorithm in the notes. And the very last topic we looked at was graph coloring. So coloring of a graph means choosing a color for every vertex, and you want adjacent vertices to have different colors. All right, so we saw this with bipartite graphs, coloring them with just two colors, but most graphs will need more than two colors. The chromatic number of a graph this notation, Greek letter chi of G, means the chromatic number. That's the smallest number of colors you need to color the graph G. Okay, so that's two definitions, coloring and chromatic number. So just the main thing to remember, that if two vertices are connected by an edge, they have to have different colors. Okay, so how about these examples? G1 here. Yeah, we saw this already. You can color this with just two colors are needed. So the chromatic number is 2. You certainly need at least two colors, but two colors so that every edge connects different color vertices. So chi G1 is 2. G2, the second graph. Yeah, well, we saw this. Whenever you have a triangle, you need 3 different colors. Maybe let's use numbers. Okay, so we need 3 colors here. And then, this could be 2 or 3. This could be 1 or 2. Yeah, but we do need 3 colors here. We can color it with 3 colors. So the chromatic number is 3. Yeah, so this is not bipartite. We needed more than 2 colors. And how about this one, G sub 3? Yeah, so here we have 5 vertices, and you can see each vertex has degree 4. In fact, each vertex is connected to every other vertex. So this is really K5. Complete graph. So we need 5 colors. Okay, so 1, 2, 3, 4, 5. So the chromatic number is 5. You could try it with 4 colors or fewer, but that's not going to work. You'll end up with an edge connecting 2 vertices of the same color. We can use graph coloring to color maps as well. So you make the dual graph of a map by giving each region a vertex, and then 2 regions with a common border get connected by an edge. And now coloring the dual graph corresponds to coloring the map so that regions with a common border have different colors. Okay, you don't want two regions that are with a common border the same color. That it'll look like it's the same region. Okay, so here's a few states on the West Coast. So if you want to color these, okay, so first make the dual graph. So each region gets a vertex. Idaho, Nevada, Arizona, New Mexico. And then if 2 regions have a common border, then they get an edge connecting them. Okay, there's no edge between California and Utah. There's no they don't have a common border. Yeah, you can see Nevada is connected to all the other states here except for New Mexico. And New Mexico, yeah, left out the other states, but it's just connected to Utah and Arizona here. So we get this dual graph. And now try to color this graph. So how many colors do we need? Yeah, you see a triangle here, so we need three colors for the triangle. Okay, so Nevada is color 3. So yeah, I'm trying to color it just with 3 colors. So then if I have a 1 and 3 here, I need a 2. This has to be 1. Yeah, but now this Arizona is connected to these 3 different colors. So I need a 4th color. And then this could be 2 or 3. Yeah, so there's no way to color this with 3 colors. You need at least, well, you need 4 colors. So the chromatic number here is 4. And the original map, yeah, you can use these 4 colors to color it in. All right, so 4 colors. And yeah, we looked briefly at the 4-color theorem. So for any map, yeah, you need at most 4 colors. And so this is the maximum. Okay, so coloring graphs is just yeah, put in colors, put in numbers, and try to make sure that every edge is connecting 2 different colors, 2 different numbers. All right, so that's a quick review of everything in Chapter 10. Yeah, you can go back to the notes on each section to look in more detail.